due to continuous system. And then we'll be doing the examples which have been previously asked in the competitive exam. We'll be doing those examples. Okay. So electrostatic potential due to continuous system. Okay. So if you have continuous system, what to do is that step down first is that we'll assume that the entire charge distribution is composed of infinitely many and vanishingly small elements. Then calculate the potential due to one such element and then integrate. Exactly same procedure as that of the electrostatic field, but the only difference is that the electrostatic potential being a scalar quantity, so it's always easier to calculate electrostatic potential compared to the electrostatic field, because in electrostatic field you will have to take care of the directions, but in electrostatic potential there is nothing like direction, so it's always easy to deal with these scalars compared to the vectors. Fine. अब यहाँ ध्यान रखो बेटा. Okay. So what I will do is simply is this. I'll first of all calculate dV, where dV is the electrostatic potential because of a small charge element that's equal to K multiplied by dQ divided by R. Like this it is. K dQ divided by R. Okay, where K is electrostatic constant, dQ is the charge of an element, and divided by R. Then if you want to calculate V, then V will be simply equal to integration of dV. Now this dQ, it will be equal to this dQ will be equal to lambda multiplied by dL, or it can be equal to sigma multiplied by dA, or it can be equal to rho multiplied by dV. It will depend. It depends upon whether it is linear charge density or surface charge density or volumetric charge density. Okay, so accordingly we can choose the element, the charge element is dQ. Fine. Now the example number 1 we have is this charged arc. Okay, so before going to charged arc, let's do this example. First of all, charged rod. If you have a charged rod, how to calculate the electrostatic potential due to charged rod? Okay, so simply the example is like this. So this is a charged rod. Okay, a linear charged rod like this. It is. Wait a moment. Okay, so for example, here we have this charged rod. This is straight charged rod, uniformly charged, fine, and we are supposed to calculate electrostatic potential at an axial point. That means at this very point we have to calculate electrostatic potential at this point P. Okay. Then what is given is this: the coordinates of these points are given. So here it's x is equal to 0. Then here x is equal to, let's suppose it is equal to L. Then here this x equal to L, and we are supposed to calculate what the electrostatic potential at the point P. Okay, in terms of Q or in terms of lambda, one and the same thing. You know, suppose the charge of this is equal to Q, and we are supposed to calculate what is the electrostatic potential at point P. We have to calculate this. Okay, so what I will do is this: I will chop this rod into many pieces. Okay, into infinitely many and vanishingly small pieces. Then I will calculate electrostatic potential due to one such piece, and then I will integrate. As simple as that. Fine. Now it's like this. For example, here we have one such element. Okay, one such piece. I'm chopping this into many pieces. So this one such piece, and the length of this I will be taking the dx, vanishingly small element, which is whose length is equal to dx. Fine. And the distance from here to here, suppose let's assume that it is equal to x. From here to here, it is equal to x. This is equal to x. Okay. Now let's calculate the potential because of this. Okay, so potential. So now this is a point charge here, whose charge is equal to dq. This element, its charge is equal to dq, and this dq will be obviously equal to lambda multiplied by dx, where lambda is a charge density. So if you want to calculate charge, that will be equal to charge density multiplied by the length, lambda into dx. Fine. And we have to calculate what the potential at the point P because of this. So that will be obviously dv will be equal to k multiplied by the charge, which is equal to dq, divided by the distance here, that's equal to what? Divided by the distance here, that's equal to x. Or we can write it like this as well. It's equal to k multiplied by lambda into dx divided by x. Like this it is. Fine. dq is replaced by lambda into dx. Okay. Now let's evaluate it. Okay, so concentrate here. Now let's solve this integral here. Okay, so potential V will be simply equal to integration of dV. Now k and lambda are constants, so pull them out of the integral. So k multiplied by lambda out of the integral. Integration of what? We are left with this integration of dx by x. Okay, so it's like this integration of dx by x. And what about the limits of integration? Obviously, limits of integration will be when this element is here at this very point, x is equal to L, and when the element is at this edge. Okay, so I can say that the value of the L, it goes from, x goes from where to where. At this point it's equal to L, and at this point the distance is equal to L. Okay, when the element is at this very point, the distance between this and this, that's equal to how much? This x is equal to this, which is equal to L, and the distance here from the point of interest will be equal to 2L. So the limits of integration will be running from where to where? From L to 2L. Not from 0 to L, but L to 2L. What's this x? X is the distance of the charge element from the point of interest. Okay, so obviously this distance from here to here is equal to L, and the distance from here x equal to 0 to point P is equal to L. So the limits of integration will be from L to 2L. And what's the integration of this 1 by x? That's obviously ln of x. So it will be k into lambda into ln of x. And then the lower limit is what? That is L. Upper limit is 2L. So obviously it is what? P is equal to, now here it is k lambda. Then it is upper limit minus lower limit. So it will be finally ln of 2L by L. Isn't it? Ln m minus ln n is equal to ln m by n. So finally it is equal to this ln of 2L by L. L and L is going to vanish. So we are left with what? We are left with ln 2. So potential will be equal to k multiplied by lambda multiplied by ln of 2. This is the electrostatic potential at point P, which is at a distance of x from one end of the wire. Okay. Now we are done with the electrostatic potential. Fine. Okay. Now let's do one more example here. Example number 2 is like this. So example number 2 on the same, that is charged rod. It's like this. Here we have, it is given to us that this is for example a rod like this. Okay, like this it is, for example here we have a charged rod. Now this is a point of interest where we want to calculate the electrostatic potential, and its coordinates are given x is equal to 0. Here it is given that x is equal to L, and here it is given x is equal to L. Fine. Okay. Now this is a positively charged rod, but this time it's non-uniform. Okay, so here I will write down the charge density of the rod is given by this. Charge density of rod. Charge density of rod is non-uniform. Here I will write down charge density of rod is non-uniform, and varies with x as, with distance x as lambda is equal to, suppose a constant is there, alpha x plus beta, something like this, alpha x plus beta. Fine. And you are supposed to calculate. So question is like this: calculate electrostatic potential at point P. You will have to calculate what is the electrostatic potential at point P. Distance from here to here is L, and distance from this point to this point. From P to A it is L, and from P to B it is equal to 3L. Okay, so L plus this 2L. Okay, so here it is L, and this also L, so it is 2L. Fine. Now again, what I will do is this: I will again assume that it's made of infinitely many and vanishingly small elements. So this one such element. Fine. And this element, its charge is equal to dq, and this dq will be obviously in turn equal to lambda multiplied by dx. Fine. And the separation from here to here, that will be obviously equal to x. Suppose that's equal to x. Okay, distance of the element from the point of interest is equal to x. So we will calculate what's the electrostatic potential because of what? Because of this, we'll calculate electrostatic potential because of the charge element, and then I will integrate here. Okay, so I will write it like अच्छी तरह से यहाँ ध्यान रखना बेटा. Okay, so dv will be what? That will be equal to k multiplied by dq divided by distance, which is equal to x. dq will be replaced by lambda into dx divided by x. Then this lambda will be also replaced like this. dv is equal to k multiplied by lambda के बदले क्या लिखेंगे? Lambda is in turn equal to alpha x plus beta. Alpha x plus beta. Okay, divided by x here. It's like this, divided by x. Okay, with respect to x, something like this. Okay, so here lambda is given, that's equal to alpha x plus beta. So here I am writing it is alpha x plus beta divided by x. Okay, then I have to integrate. So v will be in turn equal to this k multiplied by integration of x divided by x, that's equal to 1. So alpha plus beta by x. Okay, with respect to x. And whatever the limits of integration will be obviously from where? From x equal to L to x equal to 2L. Okay, so here x is equal to the distance between the point of interest and the point A is equal to x is equal to L, and the distance of point of interest P from the point B will be equal to 2L. So the limits of integration will be obviously from L to 2L. Okay, L to 2L. But the potential here finally will be this. Concentrate here. So what is the potential here? The potential will be finally equal to this. V is equal to k is a constant, keep it as such. Integration of alpha is obviously equal to alpha x. So it will be something like this: alpha x plus beta into ln of x. Okay, then what about the limits of integration? They will be from L to 2L. Okay, then it will be like this. So V potential V is equal to k multiplied by this here upper limit minus lower limit. So 2L minus L, that's obviously equal to L. So यहाँ आएगा बेटा alpha into L plus यहाँ आएगा beta ln 2. So this is the answer. Okay, so this is the electrostatic potential at point P. Okay, so one example on first is based on the uniform charged rod. If this is a uniform charged rod, so you can calculate what is the electrostatic potential at point P. Okay, and then the limits can change. In the different examples, the limits can change accordingly. You will have to do it. Okay, example number 2 is what? It is non-uniform. In case it is non-uniform, I'm sure you can do it. Okay, now it's not necessary that always the alpha will be equal to this lambda will be something like alpha x plus beta. It's not always necessary. Okay, so let me keep home assignment for you. Example number 3 will stay as a home assignment, and that's like this, that this lambda is equal to, exactly for the same problem, lambda is equal to alpha into x square plus beta x, something like this, alpha into x square plus beta x. Fine. Okay, so this is here what coulomb per meter. This is the charge density that is given to you, and you are supposed to calculate potential at point P for exactly same problem like this. Yes, so here we have this rod, and this here point of interest, which is point P, and this here x equal to 0. Let this be x equal 2L, and let this be x equal 3L. Okay, x equal 2L and x equal to 3L. Then this is positively charged, which is non-uniform, and it's given like this, alpha x square plus beta x, where alpha and beta are constants, and you are supposed to calculate potential at point P. You will have to calculate this. Okay, now this will be a home assignment for you. I'm sure you must be able to do it. Okay, there's no rocket science in it. Let's move back this example. That is this charged arc. Okay, we have to calculate the electrostatic potential due to the charged arc. Like we have calculated what? The electrostatic field due to the charged arc. Exactly in the same way, we will be calculating this electrostatic potential due to the charged arc. Again, I will repeat that calculating electrostatic potential is very easy compared to calculating electrostatic field. Okay, because while calculating electrostatic potential, you do not take care of the directions. There is nothing like resolution and all that. Okay, because that is true only for the vectors. So concentrate here. अब देखो बेटा how I will do it. Okay, so here we have, suppose that this is a coordinate system given to us, an xy coordinate system, and then this is a charged rod. Fine, and let's assume that it's a uniformly charged rod. Okay, so it is positively charged, uniform positively charged rod. Sorry, it is this charged arc. Okay, and it's given to us, what is given to us is this, the angle subtended by this arc at the center is equal to theta, the generalized arc, and the radius here that's equal to r. Now we have to calculate what electrostatic potential because of this charged arc at this very point, which is the point P, at the point of interest. Fine. Safely we can calculate. What I will do again is that I'll calculate the electrostatic potential because of this. So suppose that it is given that its charge density is equal to lambda. Lambda or Q is given to us. So finally you can write down the expression in terms of lambda, or you can yourself write down the expression in terms of Q as well. Okay, lambda or Q is given to you. Fine. Now this, for example, an element. Okay, suppose its charge is equal to dq. Fine. This dq will be in turn equal to what? It will be equal to lambda multiplied with its length, that's equal to dl, lambda dl. Fine. Then we can write it like this as well, lambda multiplied by dl. dl is the arc length, and that will be obviously equal to this. So this is an element, and this element, suppose it subtends an angle of d theta at the center. So this angle is d theta. Now this radius r. So arc length is obviously equal to radius multiplied by angle subtend. So that means this dl will be equal to r d theta. So this is dq. Fine. dq is the charge carried by this. It will be equal to lambda into dl, where dl is its length, and obviously we know that the length is in turn equal to r d theta. Okay, that's equal to radius multiplied by angle subtend, where angle subtended by this element will be equal to d theta. Okay, small angle. Then we can calculate the potential at this point because of this. So what's that? That's dv, which is equal to k multiplied by charge, which is dq, divided by distance, that is equal to r. Okay, perfect. Now up there, so here it is dv is in turn equal to k divided by r. This dq, it will be replaced by what? It will be replaced by lambda r d theta. Lambda r d theta. Fine. This r and r is going to cancel. So what is dv? dv is equal to k lambda multiplied by d theta. Okay. Now out of these, this k and lambda, that's a constant. Both are constants. And what's variable is this d theta. Okay. So this d theta is a variable. So v will be equal to what? It will be equal to k into lambda into integration of d theta. Okay, limits of integration will be simply from 0 to theta. Okay, because had this element been here, then the theta is equal to 0 degree. Then for the element when it's here at this point, theta is equal to theta. So the limits of integration will be from 0 to theta. So potential V will be simply equal to k lambda theta. That will be simply equal to k lambda theta. Okay, so this in terms of charge density and angle. Okay, so here I can write down in terms of charge as well. What I will write is this charge is equal to lambda is equal to charge per unit length. Or I can write it like this, q divided by L is the arc length, that is equal to radius multiplied by angle subtend, or theta. I can write it like this, where L is the length of this. So obviously length is equal to what? That's equal to radius multiplied by angle subtend. L is equal to r theta. Fine. That means I can write it like this as well. V is equal to k. Lambda के बदले क्या लिखेंगे बेटा? Q divided by r multiplied by theta. Then here it is theta. Theta will cancel. So potential V will be equal to what? So this implies that the potential V will be equal to kq divided by r. So we can write it like this as well. Kq divided by radius, or it's equal to k lambda theta. So it will depend upon If lambda is given to you, then this is the answer, and if charge is given to you, then this is the answer, kq divided by r. So we are done with the electrostatic potential as well. Fine. Okay, then you can do a couple of examples here like this, which are as special cases. For example, if there is one quarter of ring or there is semicircular ring, how to calculate the electrostatic potential at the center point. Okay, like this it is. For example, here we have, this is the example. It's like this. Suppose that here we have a semicircular ring like this it is. This is semicircular uniformly charged ring like this it is. Okay. Then you are supposed to calculate what electrostatic potential at point P. You will have to calculate what the potential at point P. This is a uniformly charged. Okay, now we know what's the electrostatic, we know what is the theta, so I can write it like this, kk badle likhunga beta 1 by 4 pi epsilon naught multiplied by lambda will be replaced by lambda, and theta will be replaced by what? That will be replaced by pi, because the angle subtended here, that's equal to pi. Okay, so pi and pi will cancel, so potential at point P is simply equal to what? That's equal to lambda divided by 4 epsilon naught. So I can write like this. Okay, or I can write in terms of charge as well. Lambda is called charge per unit length, so it will be q divided by 4 epsilon naught multiplied by length of this, and length is equal to what? That's equal to pi r. So I can write like this, pi r. So I will also write it like this, q divided by 4 pi epsilon naught multiplied by r. Like this I can write it. Right? So this is the answer, lambda divided by 4 epsilon naught, or this is also the answer, q divided by 4 pi epsilon naught multiplied by r. Okay, so this is the electrostatic potential because of semicircular ring. Right? In the same, we can do this example as well. Suppose that if we have a circular ring like this, it is uniformly charged circular ring, and you are supposed to calculate potential at the center point. That means we have to calculate potential at point P. So this is the radius which is equal to r, and this is a uniformly charged ring. Okay, uniformly charged ring. Then safely you can calculate what the potential at this very point, so you can calculate it. So the potential at the point P will be simply equal to what? That will be equal to k multiplied by q divided by r. Simply you can write like this. Okay, by k is in turn equal to 1 by 4 pi epsilon naught multiplied by q divided by r. Or there is one more way to calculate potential. So here I will write down that potential at point P in terms of lambda is equal to k lambda into theta. A के बदले क्या लिखेंगे बेटा? 1 by 4 pi epsilon naught. Okay, lambda is equal to lambda, and theta here angle subtended will be equal to 2 pi. So 2 will cancel this, so it's also equal to lambda divided by 2 epsilon naught. Okay, so we are done with the what? With the arc. So simply what you'll have to memorize, which equation you'll have to memorize is this, k lambda theta, the electrostatic potential at the center of a semicircular of an arc, simply of a
Voice is not coming, sir. Voice. You are inaudible.
okay. So we are done with what? With the arc. Okay, if we have semicircular, we have circular arc. Simply the electrostatic potential because of circular arc is equal to k lambda theta, or it's called k q divided by r. So enter the both lambda as well as this. Okay, so we are done with this example. Next example, this one is also important because a question has been asked on this. like this it is. Okay, so we have to calculate what this is a charged ring. Now we have to calculate electrostatic potential because of the charged ring. Okay, for example, it's like this. This is a charged ring here, uniformly charged ring. Fine. Now this is a uniformly charged ring. The charge carried by this is equal to Q. Okay, and its radius is equal to suppose A. Suppose this is the radius which is equal to A, and the distance is equal to X of the point of interest. At the point P, we have to calculate what electrostatic potential. Okay, so what I will do is this. I will again assume that it is made up of infinitely many and vanishingly small elements. Then I will try to calculate the electrostatic potential because of one such element, and then integrate to calculate the net electrostatic potential, and then I will plot the graph as well. Okay, so here I am going to do it like this. It is. Now what's the electrostatic potential? Because suppose that I will assume that here is a charge element which is equal to dq. Okay, and obviously the distance from here to here will be equal to this, which will be equal to under root of x square plus a square, x square plus a square. Fine. Now what I will do is electrostatic potential at point P because of this element. So dV will be equal to this. It will be equal to k multiplied with the charge, that's equal to dq, divided by the distance square. So sorry, distance only, that will be equal to root of x square plus a square, isn't it? Electrostatic potential because of point charge is equal to kq divided by distance. Okay, so here what is the distance between this point and this point? That's equal to under root of x square plus a square. Then we want to calculate net potential, so net will be equal to integration of dV. Okay, now how many elements are here on the ring? There are infinitely many number of elements on the ring, and all those elements are equidistant from the point of interest. That means root of x square plus a square is constant for every element. Okay, so that means this root of x square plus a square, and the integration of dq will be okay. So potential will equal to what? That's equal to kq divided by root of x square plus a square. Fine. You can calculate field from here as well. If you are interested in calculating field, you can calculate field from here as well using this equation, that field is equal to negative gradient of potential. So we can write like this, minus dV by the electrostatic field, and it will come out to be that kq multiplied by x divided by x square plus a square, like this. Fine. You can do it as a home assignment. Okay, so you will do this as a home assignment. Then that means first of all the potential you can calculate, and then from there taking its negative gradient you can calculate the electrostatic field. This is one more way by which we can calculate the electrostatic field. Okay, one is integration, another is this, the negative gradient of this potential. Okay, fine. Electrostatic potential because of this, that's simply equal to kq. I will write like this, that the potential because of the ring, here I will write down potential because of the ring is simply equal to k multiplied by charge, that's equal to q divided by hypotenuse. Simply I can write it like this, divided by hypotenuse. Okay, or the slant height of the spoon, simply like this, the hypotenuse of the point of interest from the ring, that's simply like this. Okay, hypotenuse, you can memorize it like this, that it will be integral equal to kq divided by hypotenuse will be equal to under root of x square plus a square. Okay, so this is the electrostatic potential due to the ring. Fine. Okay, now next is that let's do here this, that is we have to plot v as a function of x versus x graph. Let's plot this graph. Okay, we have to plot this graph. Okay, so let's plot the graph. Okay, in order to plot the graph, we have to make some preparations. First of all, point number one is this. What's v of x? V of x is equal to this. That's equal to kq divided by root of x square plus a square is for 3/2. Point number one. Okay. Then point number second is this. Point number second is this. Is this function an even function or odd function? It's obviously an even function. Okay, because when I will substitute x equal to minus x, so it will become positive. Okay, so that means it is an even function. So here I will write down it is an even function. When it's an even function, that means when it's an even, it's not an odd function, but it's an even function. It implies that v of plus x is equal to v of x, and v of minus x is also equal to v of plus x. Fine, v of plus x is plus times v of x, and v of minus x is also plus times v of x. So that means the graph will lie in the, this implies that the graph will lie in the first and second quadrant. First and second quadrant. Graph will lie in the first and second quadrant. Fine. And moreover, next is this. If x is equal to 0, if x is equal to 0, what's the electrostatic potential? Ab dekh lo beta. When at the center point, is the electrostatic potential 0 or not equal to 0? Okay, electrostatic field, we know that that's equal to 0, but the potential is not equal to 0. Because when x is substituted as 0, 0 square plus a square is simply a square, root of a square is a. So the potential at the center point is simply equal to v is equal to kq divided by a. And where a is the radius of this, as expected, this is the potential. And this potential is the v max, this maximum potential. Fine. And point number third is this. If, for example, this x is very large compared to A. If X is very large compared to A, that means safely what you can do is this: you can neglect A square compared to X square. So the potential in that very case will be equal to K cube by X, which implies that the potential is proportional to 1 divided by X. That means the graph must be a rectangular hyperbola. Okay. Now collecting all this information and then trying to plot the graph. Okay, I will collect all the information and then I am going to plot the graph. So point number one is that it is an even function, means that it will lie the first and second quadrant. Point number second, if x is equal to 0, potential is maximum. Okay, so that means if we will draw a tangent when x is equal to 0, if I will draw a tangent to v of x curve, it must be a horizontal. Okay, this tangent must be horizontal. And number third is that if x is very large compared to A, then in that very case potential will be proportional 1 by x, which means that it must be a rectangular hyperbolic graph. Okay, now collecting all the information, that means the v of x versus x graph must be something like this. It must be something like this. So here it's v as a function of x versus x. Okay, and the graph will be like this. Okay, so obviously the graph will be like this. Bell-shaped curve, something like this. Okay, where this is v is proportional to 1 divided by x, and here it is maximum. So here the potential v is equal to kq divided by a, kq divided by a. Okay, so we're done with. Moreover, it's an even function, implies that it lies in the first and the second quadrant. So there's the first quadrant and the second quadrant. Obviously, the graph lies in the first and second quadrant. Right? Okay. Up there, next. So this question has been nice 2008. Now we can this example safely. The question is a loop of radius r. There is a uniform charge density. There is a uniform charge density. The ratio of the potential at height 2r on the axis to that at the height 3r is. Okay. So what you have to calculate is this. Okay. So there's what. First of all, there's a loop of radius r and it gets a uniform charge density. So first of all, write down what's the potential at distance x. Potential at distance x is simply equal to k divided by hypotenuse. And what's hypotenuse? Under root of x square plus a square, where a is the radius. Fine. Okay, now concentrate here. How I will do it. Okay, so what the potential as a function of x? Potential as a function of x is what? V as a function of x is equal to k q divided by hypotenuse. And what's hypotenuse? Under root of x square plus a square. Fine. Okay, now it is given to you that the a here that's equal to r. Okay, and then I will calculate what the potential at the point 2r at height 2r. That means we have to calculate what the potential at 2r. Obviously, potential at 2r will be equal to kq divided by x will be substitute. X will be replaced by 2r. 2r whole square will be equal to root of 4r square, like this. And a will be replaced by r, so it's plus r square. So that means it is something like this. It's equal to kq divided by root 5 multiplied by r. So it will be root of 5r square. So r square will be out of the square, so square root, so it will be root of 5r. Then let's calculate the potential at r. So potential at r will be simply equal to kq divided by x के बदले क्या लिखेंगे बेटा r square plus r square, so that will be equal to root 2 multiplied by r, something like this. And then sorry, we have to calculate potential at what point? At point 3r, I think. At 2r and then at 3r. So potential at 3r, so it will be like this. Wait a moment, it will be something like this. So here it will be 3r, so 3 x के बदले क्या लिखेंगे बेटा 3r, so 3r square is 9r square, 9r plus 1, that's equal to 10, so it will be root 10 r. Now we are supposed to calculate what? The ratio of these two. We have to calculate the ratio of these two. So safely we can calculate. We have to calculate what's the potential at 2r divided by potential at 3r. Potential at 3r, it will be something like this. So potential at 2r is equal to this, kq divided by root 5r, and then this. Okay, so here I will write down kq. So here I will write down kq divided by root 5 multiplied by r divided by kq divided by root 10 r. So root 10 multiplied by r. Okay, so what will cancel is this kq by r will cancel, so root 10 is going here, so it will be root 10 divided by 5 divided by root 5. So this is the answer to the problem. Okay, so that means v at 2r is v at 3r is equal to what? That's equal to root 10 is to root 5. Okay, or you can safely write it, it's equal to root 2 is to 1, because root 10 can be recognized root 5 into 2, so root 5 and root 5 is going to cancel, so it's simply equal to root 2 is to 1. Okay, now we are done with this. We have calculated electrostatic potential because of this as well. Okay, here I'll be giving a Humason for you, and that's electrostatic potential because of this. You know what's the electrostatic potential because of the ring. Using that expression, you can safely calculate what's the electrostatic potential because of the disk. Okay, so that will stay as Humason for you. So here I'm going to write that calculate electrostatic force. So here I will write on this home assignment for you, and I believe that you must be doing these home assignments at your home. Okay, so question is like this: calculate electrostatic potential due to uniformly charged disk. You have to calculate electrostatic potential due to uniformly charged disk. Okay, so this is stage of home assignment. Fine. अब देख लो बेटा, next example is this, that we have an infinite charged sheet. We know that the electrostatic field to the infinite field. This time we have to calculate what electrostatic potential. Okay, we'll calculate the electrostatic potential of the infinite charged sheet using the electrostatic field. Okay, so देखो बेटा कैसे. It's like this. Here what we have is this is a sheet here. Okay, this is an infinitely charged sheet which carries a charge density of plus sigma. Surface charge density uniform, that's equal to plus sigma. And then we have to calculate electrostatic potential at this 3 point, which is point P. At this point P, we have to calculate electrostatic potential, which is at a distance of, let's suppose that, let's assume that these distances are, we know electrostatic field at this point will be in this direction, and this electrostatic field will be obviously equal to what? That will be equal to sigma divided by 2 epsilon 0 multiplied by r cap. Can I write like this as well? So it's like this. In this direction, it is directed, so sigma by 2 epsilon 0 multiplied by r cap. We have to calculate electrostatic potential at this 3 point. So let's try to calculate what? Electrostatic potential at this 3 point. Okay, तो अच्छी तरह से यहाँ ध्यान रखना बेटा. Okay, so concentrate here how to calculate electrostatic potential at the point P. So let's write out. Concentrate here. What I will do is this. I will use this equation that V. I will try to calculate what. Okay, let me calculate V at R will be equal to what? That will be equal to minus times integration of E dot dr. Something like this. E dot dr. Okay, now obviously E and dr, they are parallel to each other, so obviously it will be equal to minus times integration of E multiplied by dr. This is the potential at any point which is equal to R. Fine. Then I can write it like this: V at R will be equal to minus times integration of E will be replaced by sigma divided by 2 epsilon naught multiplied by R. Fine. Okay, then the potential here finally I will write like this: V at R will be equal to sigma by 2 epsilon naught is a constant. Integration, sorry, this is dr. Integration of dr is simply equal to R. So that means it's equal to minus sigma R divided by 2 epsilon naught plus a constant of integration, that's equal to C. Okay. Now what does this C implies? What does this C implies? It actually implies a reference point here. Okay. Suppose that here we have some reference point. Okay. So that reference point is actually what happens in case of this sheet. In case of sheet, the electrostatic potential at the infinity is not equal to 0. So in this very case, infinity is not what. That's not the point of that's not the point of zero potential, infinity. So infinity is not the reference point. Why? What is the reason? So what this negative sign implies that the electrostatic potential, for example, if you want to calculate what is the electrostatic potential at infinity, so substitute the value of R equal to infinity. So यहाँ infinity आएगा. So obviously V at R equal to infinity is not equal to 0. That's not equal to 0. Fine. So that means infinity is not a reference point, first of all. Okay, because when you substitute R equal to infinity, it will not be equal to 0. That means the infinity is not a. So this implies that infinity is not a reference point. Not a reference point for a sheet. Not a reference point for a charged sheet. A reference point for charged sheet. Fine. Charged sheet. Okay. Now what about this C? This constant of integration. It will take care of what? It will take care of this this reference point. It takes care of the reference point. Fine. Okay. So what I will write is this. I will write down here a reference point here. For example, that's point O, something like this. The point R, like this. Okay. So that reference point, this constant of integration will be taking care of that. Okay. So this is C. Fine. Okay. Which in turn implies that the electrostatic potential will not be equal to 0 at infinity. Okay. Great. Now next is that if you want to calculate delta V, the electrostatic potential, what this negative sign implies here. Point number 1 is this clear to you? I think. Point number 2 देख लो बेटा. If for example there's a ये याद रखो ये point. If for example there's a point charge and electrostatic potential due to the point charge, you know that electrostatic due to the point charge is KQ divided by R. That means the electrostatic potential as R increases, it dies down. Okay, it dies down with the distance. Okay, this negative sign here also implies that the electrostatic potential it decreases with the distance. अच्छी तरह से यहाँ ध्यान रखना बेटा. For example, suppose that what I will do is this: I'll place a charged particle somewhere here. This is a charged particle, positively charged particle. Now, obviously, this positively charged particle, it's initially at rest, and it will experience an electrostatic force of repulsion because of the sheet. Fine. Now, because of the force of repulsion, it will accelerate in this direction. And after covering some distance, suppose the charged particle reaches here, it will have some non-zero velocity, v which is not equal to 0. Initial velocity is equal to 0. It starts from rest and finally attains some velocity. Now, the question arises, where from this velocity this kinetic energy comes. Okay, for example, it has some mass as well, so it has some non-zero kinetic energy. Initial kinetic energy is equal to 0, final kinetic energy is not equal to 0. Now the question arises, where does this kinetic energy comes from? Okay, and the answer to the problem is that the kinetic energy is actually coming from where? The potential energy. Okay, so actually as the charged particle goes from point A to point B, the electrostatic potential decreases. Okay, a charged particle always moves from a high potential energy to a low potential energy on its own. On its own, it always moves from high potential energy to low potential energy. That means as it goes from A to B, so the kinetic energy potential at the point A must be greater than the potential at the point B, isn't it? So that means as R increases, okay, the distance from the charge sheet increases, the electrostatic potential decreases with the distance. That is what this negative sign implies. This negative sign, so here I am going to write this, that negative sign implies potential decreases. Potential decreases as R increases. Potential decreases as R increases. Here I can safely plot the graph. This equation is of the form y equal mx plus c. That means it will be a straight line with the negative slope and positive intercept. Okay, so if you want to plot the graph, you can plot the graph like this. So you can plot the graph here. Let me plot the graph here. Okay, so here you can plot the graph. Point number 3 is this: plot V of R versus R graph. V of R versus R graph. Say if you can plot it, it's like this. This V of R is equal to what? That's equal to my integration more one. यहाँ और एक point आपको याद रखना पड़ेगा बेटा. You know that the electrostatic field is negative gradient potential energy. If you calculate negative gradient with respect to R, so this will be here minus will be positive, sigma by 2 epsilon 0. In differentiation of R with respect to R is 1, differentiation of constant is 0. Simply electrostatic field will be obviously equal to sigma divided by 2, actually due to the infinite uniformly charged sheet. Fine. Okay, now we can simply plot the graph. The graph will be like this. When R is equal to 0, potential becomes equal to C, which is a constant. So this is V as a function of R versus R. Okay, so when R is equal to 0, then the potential will be equal, so it will be like this. Here it will be. Fine. Now this is this here intercept, so which is intercept this here C. So the potential here when R is equal to 0, potential is equal to C. Okay, and what about this point? This point here, this will be here slope, so this is here theta, and this tan theta will be equal, you want to calculate that will be equal to sigma divided by 2 epsilon naught. Now this is equal to C, so that means this has to be how much? This has to be equal to, so that this divided by this must be equal to sigma by 2 epsilon 0. So this must be something like it must be what? This is at this very point, what's the VR that's equal to 0? When VR will be equal to 0, so that means sigma R divided by 2 epsilon 0 will be equal to C, and R will be equal to 2 epsilon naught multiplied by C divided by sigma, something like this. Okay, and if you will calculate that, we will be equal to 2 epsilon naught C divided by sigma, so obviously it will be equal to sigma divided by 2 epsilon naught. Right? That's equal to this, tan theta is equal to this. Okay, rather it is minus sigma divided by 2 epsilon naught, which implies that its slope is negative and intercept will be positive. Okay, so we have calculated. Again, I will be repeating this. अच्छी तरह से यहाँ ध्यान रखना बेटा. Infinite charged sheet, electrostatic field we know. We can calculate potential using this equation. Okay, by this or this